Right, thank you. So since nobody is willing to take my slot, you have to stuck with me. So, no, he refused, like, to my face. Yeah. So, yeah. You heard a lot about CHY and scattering equations, which are basically building some connection between worldsheet and the kinematic space amplitudes. But towards the end of the talk, last lecture, you hear that we can actually better view the amplitudes on kinematic space side as some forms, right? They're very natural, they live on their own, and they naturally come from this push forward of some forms on the worldsheet. So is there a purpose of life for those forms in kinematic space just by themselves, like without even thinking about amplitudes or worldsheet? So this is the topic of this lecture. Now I'm going to introduce you this kinematic sociohedron. And in the second part, I'm going to make a connection with the worldsheet and the CHY scattering equation you heard before. So this belongs to a broader context that you want to consider positive geometries, or just, if you can just think of them as generalization of polytopes that directly live. You heard about these positive geometries like the positive Grassmannian and so on in some auxiliary space. But more recently, you are start to thinking of them directly in kinematic space, where the amplitudes actually live. So here I'm talking about the kinematic space of Mandelstam, right? And I want to build some positive geometry, or in this case, it's just a classic polytope called a sociohedron in this kinematic space. And whenever you have a positive geometry, it's associated with a canonical form, or in the Grassmannian case, it's usually called the volume form. So if you have a positive geometry, you can think of the canonical form is defined as that it has only logarithmic singularities at the boundaries of this P. And whenever you have a logarithmic singularity, that you can compute the residue at that boundary of this canonical form, it's defined as the canonical form of that boundary, which is again a positive geometry. So in the definition of positive geometry, you need to just think of polytopes. It has all kinds of co-dimension boundaries, and every one of them is by itself a positive geometry. So this way you go all the way down to vertices of your polytope, zero-dimension boundaries, and there the residue is just plus or minus 1. So this is the D-log form, the volume form you've all heard about. Okay. So in this broader context, I want to go to a specific case that I consider, first of all, the Mandelstam space, where I want to find a positive geometry there. It's this sociohedron or Stashev polytope. I actually showed you two examples. This is the one-dimensional Stashev polytope, and this is the two-dimensional one. This is just a line interval, and this is a pentagon. So I'm gonna explain that in a second. What are these polytopes? And then you want to find the canonical form there, which turns out to be the form I introduced to you yesterday. They correspond to a way of encoding the Bayer-joint phi-cube amplitudes. Okay, so that's the plan. So our space. Before I introduce the polytope, I think it's useful to just look at kinematic space again. This time we want to give an intrinsic ordering to the whole problem. The whole problem have an intrinsic ordering, say 1, 2 to n. That you can view the whole problem as giving so the kinematic space can be viewed as spanned by the planar variables that we talked before. So if you have an n-gon, let's associate the momentum to this n-gon. Say here this P1, P2. Let's call this vertex 1. So this is Pn, and so on. Okay. So your momentum is conserved. It forms a n-gon, and these vertices are like 1, 2, 3, and so on. Okay. So what I mean by kinematic space, which we already talked about, the space spanned by Mandelstam in large enough space-time dimension, such that they only satisfy linear relation as the momentum conservation, can now be just viewed in this way. Okay, I just list all the planar variables are variables connecting two vertices in this n-gon, like I and j. For every such diagonal of your n-gon, I have a variable xij. Okay? To connect to our old story, this xij is nothing but the sum of the momentum in between. So in this case, if this is I, this will be just pi minus 1, and this is pi, and so on, and this would be pj minus 1, right? So we're just summing over all the momentum in between pi plus 1, all the way to pj minus 1 squared. That's our planar variable that, as we discussed yesterday. Now I'm just associating every such variable to the diagonal of an n-gon, and how many variables we have there, it's the dimension of this space spanned by them, the kinematic space, is just n minus 3 over 2. That's the number of diagonals for an n-gon. Okay? So of course here by momentum conservation you could also take the sum of this momentum squared. That gives you the same thing. So these are our basic variables. They are also just all the poles that can appear in a planar ordered amplitudes. They are the planar poles. So this is our space. We want to build so this is a very high dimension space. In this space, for n particle scattering, we want to build a n minus 3 dimensional polytope called a sociohedron. Okay, n minus 3 dimensional sociohedron that now I'm gonna introduce. So combinatoric speaking, this sociohedron just has the property that it's a polytope, and its boundaries are in one-to-one correspondence with some triangulation of an n-gon. Okay, so if it's an n minus 3 dimensional sociohedron, say in the 4-point case, so this is the first case is actually n equals 4. Then it's one-dimensional. You can view the inside of a sociohedron as just not doing any triangulation. The square itself, the n equals the foregon, and now it's two endpoints, these two boundaries corresponding to two possible triangulation of your n-gon. So if you're using our variable, this one would be, let's put some number here like 1, 2, 3, 4. Then this endpoint will correspond to x13 equals 0 in the end, right? It's labeling this this boundary, and this will be x24 equals 0. In our usual language, this is our s, and this is our t. Okay? And in this case, all the vertices of your sociohedron corresponding to a full triangulation of your pentagon. And how they are organized this way is that every two vertices, when they share a edge, it's really just a mutation between the two. So actually for every codimension 1 boundary, it's a partial triangulation. In this case, it's this guy. That it has only this diagonal. Okay? And in this case, you can work it out. It's this guy. That the diagonal shared by them, it's this guy. And this one for the edge. And what's this? This one. Okay? So this is this inside of the sociohedron has 5 codimension 1 boundaries, which are corresponding to one of the 5 diagonals going to 0. These are the 5 boundaries, or 5 planar poles. And when you go to codimension 2 boundaries, it corresponds to 2 xij's going to 0, which will be our cubic graph. You know, you go to further. So the dual graph of such triangulation give you cubic graphs, the planar Feynman diagrams, and so on. Okay? So combinatoric speaking is very simple. If you go to 6th point, you just see a 3-dimensional thing. I'm not gonna humiliate myself by trying to draw it. It has like 3 squares and 6 pentagons. They correspond to the 9 diagonal of your hexagon. You have 3 long diagonals and 6 short diagonals. Okay? So this is just combinatorially speaking. This is mathematicians know such things since the 60s, and they know how to realize them and so on. But what I'm going to talk today is really how to realize them in the kinematic space, in this space. Okay, it turns out to be a very simple way to do that, which is you take, so essentially here you see what you need to do, right? So you have the high dimensional space where you know the singularities of your object is going to be when one of these guys going to 0, the facets of your polytope. So you want to consider this simplex or this cone in the kinematic space defined by all the xij greater or equal to 0. So this is just some cone in your space. And now you want to find the subspace. So this is still top dimensional, it's of this dimension. So our construction is that you can find some subspace that's called Hn that has just n-3 dimension, such that the subspace will be some hyperplane, some n-3 dimensional hyperplane in your high dimensional space, such that the intersection gives us this polytope. So that's the general idea. And how to define this subspace? How to find this subspace? The most natural way, I think. So the most natural way I would do it is just to do the well, let's do the 4-point example first. I mean, I realized that we did it before actually for 4-point, but let's do it again. So this is just the space by x13 and x24. As we said, this is S and this is T in the physics terminology. So this x13, x24 are just the two diagonals. So by this delta 4, I really mean this region, right? So the first quadrant where x13 and x24 are both positive. Now, by what's the subspace we discussed before? The subspace is given by, in this case, the H4. So this region is my delta 4, and the H4 is given by S plus T equals a constant. So let's call it C13 for reasons will become clear later. And we need this constant to be positive now. Okay, so this is one linear constraint on a two-dimensional space. So you lower it to a one-dimensional subspace. So in the picture, this is our H4. So it's also clear why we need it to be positive. Otherwise, they have no intersection. Okay, so when you do this, it turns out the intersection of delta 4 with H4 is what we call A4, the kinematic association for 4-point. That is nothing but this line interval. And the two endpoints are t equals 0 and s equals 0. So this is a way of realizing the combinatoric association we talked about here. It's really trivial in this case, right? So how to generalize this to higher point? I already mentioned to you in the context of the form that you want to do. There's a natural generalization, but now let's do it carefully and let me just tell you the result. So the result is you always want to take some linear combination of your x variables, like with coefficient plus or minus 1, to be some constant, to be some positive constant. And what are they? They are actually very naturally associated with the physical intuition that when you have a pi and pj, you want to consider the dot product of them. Sij or 2 times pi dot pj. They can be expressed as linear combination of xij because this form a basis of the Mendelssohn space, right? So let's just write down this. This is just since they form a basis, you can express anything in terms of them. So let's write 2 pi dot pj, which is nothing but s minus sij. We put a minus. This is very easy to show that if you use this definition, xij is given by the sum of the momentum squared. This is nothing but xij plus xi minus 1 j minus 1 minus xij minus 1 minus xi minus 1 j. Okay, so I think it's the best if I draw this picture. So if you have I minus 1 I somewhere in your polygon, and then j minus 1 j, another part of your polygon, the two edges here. So this will be my pi, this will be my pj. I can consider the dot product of them. This is given by the sum of these two diagonal of this quadrilateral. So like here, minus the sum of these two ends. Okay. So this two term is blue, and this two term is orange. Okay. So remember, these two sides are for a single momentum. So it's if you write down xii plus 1 or xi minus 1i, it's 0, right? This edges of the polygon is a frozen variable. So these are valid axes. Of course, in some special case, like in our 4-point case, this could also shrink to frozen variables than they are discard. That's why here it's only 2 terms. In general, it's always we want this 4-term thing. So this is just a transformation, right? We can express any Sij or minus Sij as this combination. Here comes the definition of Hn. Hn is simply saying, let's take that combination. Let's take xij plus xi minus 1j minus 1 minus ij minus 1 minus I minus 1j, this combination, or otherwise in physics language we call them minus Sij. Okay, let's take this combination and set it to a constant Cij. So this is our condition, which is a positive constant. And as I already mentioned yesterday in the context of the form, in general these are too many conditions. Sorry, here I and j are non-adjacent, right? So at least you want I and j are non-adjacent. But even when you have I and j non-adjacent, it's still too many. If you just look at the foregone case, you can have C13 and C24. So you don't want they are the same actually. So these combinations are not all independent. So you want to skip one particle. So let's say we want to choose all the ij non-adjacent and not equal to n. You can check that this is precisely the number of constraints that you need. So you look at all such quadrilateral of your n-gon except when they hit n. So when they hit n, you just omit them because they are not independent constraints. So this gives you the number of this gives you the hn give you the n minus 2 times n minus 3 over 2 constraints, such constraints. Only these independent ones you need to use. Then the claim is the intersection of delta n, this cone in top dimension, with your subspace Hn, this n minus 3 dimensional subspace, give you a polytope that has this combinatoric structure, and whose faces and so on are corresponding to either triangulation of n-gon or planar Feynman diagrams. Okay? Yes?
I'm sorry, why the Cij is positive, right? It's equal to minus Sij.
So in other words, I want to set Sij to some negative constant, but I want to write it in this way that they are positive. Now I'm going to show you why it's needed, that all the Cij needs to be positive constants such that the intersection of the two give you the polytope. Okay? So in this case, you can already see that I don't want to set u to some positive constant. I want to set minus u, which is s plus t, to a positive constant such that they have intersection. But in general, let me just prove it now. Well, I won't rigorously prove it, but I will show you essential observation that allow us to show that the intersection is that polytope. The essential observation is the following. So what is really the fastest structure of this polytope? So when you go to a boundary, say s equal to 0, you are not allowed to go to the boundary t equals 0, since you're already in the s. For what reason? Simply because these two diagonals cross each other. So you are not allowed to reach some simultaneous factorization or codimension 2 boundaries when 2 of the crossing diagonals hit 0 simultaneously. Same here. So all these planar variables, if you look at the adjacent 2 guys, they are never crossing each other, right? So the fact that you can reach at this point is because these 2 are not crossing, so you can reach at a further factorization or further triangulation. So what we want to see as really the first order check is if these conditions allow us to reach some crossing boundaries some boundaries where two diagonals cross. If that happens, then we're dead. We're dead, right? Because that won't give us. So this turns out to be very easy to show already from this condition. Now you want this guy to be a positive constant. So just look here. When can I mean, this condition is preventing me of hitting such crossing boundaries. Why? Because if I can hit these two boundaries at the same time, so these two blue terms both go to 0, okay? So this whole sum goes to 0. Then since all my already in my comb, everything is positive, every x is positive. So this is telling you the right hand side is negative because it's minus x. Well, you want it to be a positive constant. So this is impossible. Okay? You may say this is not enough because you only consider such special crossing diagonals, but actually you can show that these equations, they sum, they telescope sum into any quadrilateral in your n-gons that goes like, let me see what's the thing I wrote. So it goes like from A to B. So sorry, this here you can have many things, and C, D. So you can have a quadrilateral like that, where you have 4 such ordered point, and just use that condition at telescope sum. You find this condition that XBC, which is this line, plus XAD, that's this line, equals XAC plus XBD, and minus the sum ofCij's that go across these sides. Okay? So if I put an I here, a J here, so I'm summing over all the Cij where I is between A and B, J is between C and D. So this is simply a sum of the conditions above. Now I want to show it's impossible to set these two blue guys. That's most general crossing, two diagonals crossing each other. It's impossible to set them to 0 simultaneously, because if you set them to 0, you are leading to contradiction again. These two guys has to be positive, but their sum is a bunch of negative constant. Okay? So this is the way you show it. And of course, there's still some technical detail that you need to show that this exists. Actually, the cleanest way to, which is harder to explain here, the most straightforward way to show it is just show at every boundary it goes to the factorization of two smaller isotropy, which I'll come back in the end. Okay? So I hope I just convince you that if you start with this comb and go to this subspace defined by this combination equals some positive constant, you reach at the isotropy. So if it's when did I start? 45 or? Okay, great. So I think I have time. Let's do this example of 5-point. 4-point is really trivial. You see it there, right? Let's really just draw this 5-point pentagon to just get you familiar with what I just said. I think it's a fun exercise. So in the 5-point case, we have 5 variables: 1, 3. Let me write it in this weird form, weird order: 3, 5, 2, 5, 2, 4, and 1, 4. Okay, so they're actually exactly the cyclic order. So if you really put numbers here, you see this is 1, 3, 3, 5, 2, 5, 2, 4, 1, 4. You can do it this way. We want all of them to be positive. Okay, that's what we have to begin with. The comb. And now we want to go to a subspace of these conditions, so we can actually, so the top dimensional space is 5-dimensional. You want to put 3 constraints such you are in 2-dimensional space. So you actually express 3 of them in terms of 2 that you choose. Say we choose 1, 3, and 1, 4 as our basic thing. So in the 2-dimensional space, we'll use say 1, 3, and 1, 4 as our coordinate, as our basis. Now you can just solve these conditions that I wrote there. Okay, that this combination is Cij. The result is very simple. You can do it, I think, in 1 minute. That you find x35 is given by this combination, I want to express everything in terms of 1, 3, and 1, 4 because it's two-dimensional, and also the constant, okay? So this is what I have for 3, 5. For 2, 5, what I have is x13 plus c13 plus c14, and for 2, 4, it's x14 minus x13 plus c13, okay? So really, my space, my polytope, in this case pentagon, is carved out by these 5 inequalities in terms of just 1, 3, and 1, 4. So let's look at it. So x14 positive, say this line is x14 equals 0, then x14 positive is here, x13 positive is here, and then this is the line that x35 is 0. So it's x35 is given by this. So it's positive gives you this. x25 is this line. Of course, here you have some number like c14 plus c24, and here you have c13 plus c14. So it's positivity giving you this side of the space, and finally this x24 equals 0. It's this line. Its positivity is giving you this. Okay. So this is how you explicitly you just plug in my conditions and ask Mathematica to plot. It gives you this region. Okay, it's really trivial exercise. Now you can do something slightly non-trivial if you're interested to write down the 9 inequalities for 6 point. It will plot you something that I was unable to do that on the blackboard. Okay, so that's the 3-dimensional isodrohedron. So this is just a way of constructing the isodrohedron in kinematic space, such that in the end we realize, every facet of our isodrohedron corresponds to a physical factorization pole. And if you go further and further, every vertex in the end corresponds to a cubic Feynman diagram, planar cubic Feynman diagram, right? So how to turn this into something we are more familiar with, the amplitudes, or at least the form we talked yesterday, we compute its volume form, or its canonical form, just as defined there. So you really want to find the form that the form lives everywhere, but the form when you go to this space, the form only has singularities when you have some boundaries here. Okay, so the singularities only lie in these 5 places. Or in the 4-point case, the form should only have singularities on this 2 point. So how to write down this form? Let's again do the 4-point example very trivially. So you can use any of your favorite coordinate like s. So you want a form that has logarithmic singularities at s equals 0 and t equals 0, where t is actually given by c minus s, right? So really the canonical form is trivially to write down like that, ds over s and minus ds over, sorry, so it's actually ds and then 1 over s plus c minus s, so 1 over c minus s. Or it's minus, sorry. It's minus. No, it's plus, sorry. so this is, if you now say that this is just the pullback of the thing I wrote yesterday to the subspace that, s plus t is c, right? So this is the canonical form of this interval. And you can check that you have logarithm singularity here, and you don't have logarithm singularity at infinity, exactly because of this sign. So this is only logarithm singularity at these 2 endpoints. So this is your canonical form. In this case, you really just find your omega of A4 is this guy. Okay? So in general, it can be a very difficult problem, like in amplitude or other more complicated cases, to find the canonical form of your polytope. But in the case of your positive geometry, but in the case of polytopes, especially in the case of simple polytopes, it turns out to be very simple. So let me just tell you the one canonical way of writing down the canonical form of a simple polytope, which turns out to be our amplitude. Okay, so it's just for a simple polytope. Simple polytope means that every vertex has exactly d facets adjacent to it. So when it's a d-dimensional polytope. So for this thing, you can simply write the canonical form as summing over its vertices, and for every vertex you just wedge together the d log of the variables associated with the faces that's adjacent to this vertex. So in our case, it will be n minus 3 such facet that touch this vertex with a possible sign that reflects the orientation of this. So where does it come from? This comes from the fact that you can write a canonical form, so you can check this guy only has logarithmic singularity at those places and so on. This is the correct canonical form. And the reason behind this is you can triangulate the dual isotropyhedron in a canonical way. So if you draw the dual of your pentagon, now every vertex turn to a edge and every edge turn to a vertex. And now you just say you draw the dual isotropyhedron like this, dual pentagon like that. So here you have 5 vertices now corresponding to the original 5 axes. So let's call it W13, W35, W24, W25, and W14. So these are the 5 vertices of your dual isotropyhedron. Then now you want to the canonical form you want to compute is just the volume of this, in this case the area of this dual pentagon. And the canonical way to compute its volume is to put some W star here and then triangulate like that. Okay? So now when you compute the volume of this guy, you're just summing over all the volume of simplices associated with every facet of your dual polytope, which is every vertex of your original polytope. So that's why you're summing over vertices of your original polytope, with this guy being the volume of the simplex associated with that dual facet of your vertex. And then this reflects the orientation in a way that there's a sign when you compute this guy. So this is nothing but what we wrote down yesterday. You can view it as summing over all the planar graphs with some sign, because every planar graph is a vertex of our isotropyhedron, and then you wedge together the d log of propagator x variables associated with this graph. I mean, in this graph, if you want, or the propagator xi, that I is the propagator of the graph, edges of the graph. Okay. So this is exactly how you reach at our projective form. If you remember planar scattering form we wrote yesterday, literally as the canonical form. One way of computing the canonical form of our isotropyhedron is this special way, this way of triangulating the dual. Okay? Yes.
4 into 5 slopes there.
2, 4, and 2, 5. Very good. Thank you. Yes. Thank you. Yes?
So this formula, actually, there is a formula called Briones formula for volumes of polytopes. It's kind of very similar to this one.
I see.
That this is kind of antisymmetric formula, but in Briones formula, it's symmetric expression.
So this is not literally the volume. So the volume is actually, yeah. Let me write it carefully. That the
rational functions.
Yes, I should write the rational function. So the canonical form of a polytope equals the wedge product you pull out, because now you are in a subspace, you can just pull out this wedge product, times something we call times this rational function, which is really the volume of the dual polytope. So this formula is still writing down the whole form, but if you pull it out, this is the volume, which in this case will be just summing over vertices with 1 now, and 1 over this xf's, product of xf's.
Kind of Brion form looks like kind of the dual version of this.
I see.
So it's the volume of the polytope itself, not of its dual, can also be written as a sum of vertices, but
it's a rational function.
Take a wedge,
yes.
Take antisymmetric expression, but symmetric.
Yes. So yeah. Okay.
Similar but different.
I see. Very good. So yeah, so that's this guy. This literally this volume is what we called yesterday, say M1 to N and 1 to N, right? So from now on we just call it Mn. This is the sum of all planar Feynman diagrams with propagators. So these are just scalar Feynman diagrams, cubic graphs with coefficient 1. But this coefficient 1, as we already discussed yesterday, is coming from the fact that you pull back your form such that all the wedge product become the same. You can pull it out. But now it's really realized geometrically as this dual volume, this volume of the dual tetrahedron. Okay, so what do we learn new from this? I mean, in physics, what do we learn new from this picture? You're just saying, oh, you are just having a glorified formula for such a, summing over 1 over propagate, summing over, scalar Feynman diagrams. There is something new we learn. Just as in the case of n equals 4 amplitude tetrahedron, once we have it there, we don't really know how to see the Feynman diagram representation from the geometry. It's extremely complicated, but we see any triangle, the statement is invariant. It's just that the amplitude the amplitude form is given by the canonical form of amplitude tetrahedron. But any triangulation, in practice, when you want to compute it explicitly, you can do any triangulation. So you get like BCFW type of representation or local expansion or something like that. They all have correspondence here. So surprisingly, even this is not the most general local expansion of your amplitude because you are choosing this special point. So actually, you could do this triangulation. You could just, let's see how I did it here. You can just do this. This will be more the analog of the local expansion in the n equals 4 case, where the same amplitude. So, yes.
Just a quick question.
Yeah.
About the sign there, it doesn't cancel out when you change the d log to the volume form, does it? Is it about
it cancels with the sign you pull out here, such that it all becomes +1 coefficient here.
Yeah.
Yes. So that's I think now it becomes symmetric. Yeah. Very good. So sorry. Let me write it this side. That the so you could just say what have you done? You are just saying there's some geometry, and when it comes to compute, when it comes to compute the amplitude, which you claim to be the volume of the dual, you go back to Feynman diagram. So your result for M5 is nothing but, say, 1, 3, 2, 4, 1, 3, 3, 5 plus cyclic, right? This is the formula that I just wrote down for 5 particle. But this corresponds to a special triangulation of the dual. When you compute the volume of the dual, you do this triangulation where you put W infinity and do this. You can do this. If you triangulate this, then you are summing over 3 areas of 3 triangles. Let me put it like W13, 35, 25, 24, and 14. You can easily compute such areas of the triangles. So this is equal to, this is not Feynman diagram now. This is similar to the local expansion of the n equals 4 case, that you get something with numerator. These 3 terms are nothing but the area of those 3 triangles I put there. Okay? Just for fun, I put them here that you can see. This is of course just one particular way of triangulating your dual object. There is something more exotic. Of course, now you can do this triangulation for any number of points, any way you like. It give you different representations, but there's something more exotic. You can triangulate the amplitude tetrahedron, sorry, here in this case, a tetrahedron itself, not its dual, and then compute the canonical form of every piece. That is more similar to the BCFW type of triangulation, which gives you just some quadratic pole even, not just here. This is not Feynman diagram, but they are still just simple poles. There you could get like XX kind of quadratic pole that I won't bother you with. So it's like corresponding to some triangulation of this object itself rather than any dual picture. Okay, so this is teaching you something. And for example, there's also like some property of the amplitude that you can learn from this, which is not manifest from Feynman diagram. Even I'm very surprised I can even learn something about phi cube, summing over planar graphs. But there is something that if I have time, I can explain to you later. Okay, so now let's go to the second part. How does all this have anything to do with CHY or with scattering equations? So this actually concerns a map from the moduli space to this kinematic space. But the first thing we want to say is that this is not the first time a tetrahedron is realized in in a physics-related context. The simplest association is something you guys all know about. It's just this moduli space of n-ordered points on the boundary of a disk. It's very closely related to what Jake told you about this positive, or also Alex told you about this positive Grassmannian G2n. But now you really mod out all the torus action on the columns. So the space is defined like that. You have this n-ordered points on the boundary of a disk, sigma 1, sigma 2 to sigma n, but there's an SL2R, so this is actually n minus 3-dimensional space. We call it M0n positive part. It's really just the Grassmannian, positive Grassmannian 2n, and then mod out this n minus 1 copy of torus action. So you can rescale the columns as you want, and that's modded out. And if you gauge fix, you could write it, because of this SL2, you can really fix it. Say you choose sigma 1 to be 0. So it's really about sigma 2, sigma 3, order to sigma n minus 2, between 0 and 1, and then you send sigma n to infinity, okay? So it's this space, very familiar. So the claim is the compactification of this space. The first claim is there's a compactification of this space that's exactly an associahedron. Okay, so this is quite famous from the 60s, but it's actually not so trivial to see it just from this coordinate, because say at 5 point this space looks like this. Okay, so if you draw it for sigma 2 and sigma 3 between 0 and 1, it really looks like this triangle rather than pentagon. Okay, what happens is that this is just a gauge fixed form. So if you zoom in here, you need to blow up to see that you actually have something like that. You need to do the blow up procedure to see it's a pentagon. This boundary is not seen in this gauge fixing. If you go to other gauge fixing, this boundary is seen, but something else is missing. The most transparent way that I know of to see that is an associahedron is go to the space of all cross ratios. Then all the boundaries are symmetric. You see all of them. All the cross ratio of 4 ordered points that between 0 and 1. Of course, now you have many variables. So this cross ratio satisfies some nonlinear constraints. So it carves out a very curvy shape of the associahedron. But now you see all the boundary just trivially. Okay. So this statement 1 is this is an associahedron. So let's call it the world sheet associahedron. This is something quite famous. It's really telling you if you mod out all the column rescaling of your positive Grassmannian, you see this space. So in other words, you can start with your minor AB being positive for any A smaller than B. But now if you say you have GL2 and also this column rescaling, you reach at this associahedron space. Okay. Now the second statement is also very simple, as you hear from Jake's talk, that in the upstairs, in the positive Grassmannian case, the top form, the volume form of that space is the Park-Taylor form there. So now if you mod out that's the 2n minus 4 form. Now if you mod out n minus 1 rescaling, you just reach at the n minus 3 form. So this will be the Park-Taylor form downstairs in this M0n, which I introduced you yesterday. So I won't need to show it. I just tell you the conclusion that the canonical form of this associahedron, you can also compute it, is nothing but the Park-Taylor form, which we like to write in this way: d sigma A minus sigma A plus 1, mod out the volume of SL2. But you can also write in the Grassmannian way that you really mod out SL2 times GL1 to the n minus 1 to the nth power, and the usual thing, right? So you have D2NC AA plus 1, A from 1 to n. Okay, so this is just saying it's also coming from positive Grassmannian. If you gauge fix, now this is something we explicitly see before, this dn minus 3 sigma, like sigma 2, sigma 2, 3, all the way to like 1 minus sigma n minus 2. So if you want the gauge fixed version, it's this. So this form is seeing all the boundaries. So when you go to every boundary, including those that's not manifest in the gauge fixing, when you go to every boundary of the sigma pinching of your space, it has logarithmic singularity and so on. Okay, so this is an interesting object, right? This by itself. Now, what's the connection of this old isotropyhedron that we know since 60s and this new one we just discovered, the kinematic one? The connection is exactly provided by scattering equation. But now you have to view scattering equation as a map, okay? Usually we view scattering equation as some equation that you start from kinematic space, which is way higher dimensional, and when you solve for some points on this M0n. And they don't necessarily lie on the positive part, right? There's no reason, they are generally complex solutions. But there's a very simple way to see that actually the key point is you need to restrict your scattering equation also to this subspace. Because otherwise it lives in the whole space. It doesn't mean anything to do the map. The map exists between this isotropyhedron to your isotropyhedron which lives in n-3 dimensional subspace. So let's do that. Let's pull back our scattering equation to the subspace I just defined for you, okay? So once you do that, you immediately realize scattering equation can be viewed as a map. Now it's from there to the n-3 dimensional subspace, and it's actually a one-to-one map between the two isotropyhedron. So just to remind you, the scattering equation we wrote, I mean we write before as SAB, just this PA dot 2 times PA dot PB over sigma A minus sigma B, sum over B different from A is 0. Okay, usually we write scattering equation like that, but now we want to rewrite it. We want to actually pull back to subspace. So first thing we rewrite is this is a trivial rewriting that you can write it as SAA plus 1. You pull out, you move all the adjacent guys to the left hand side for every equation, and this side you just have some Sij over sigma ij, where I is between 1 and A, J is between A plus 1 and n minus 1. Remember, in doing this, I sent sigma n to infinity, but it doesn't matter. You can always recover SL2C by putting sigma n back. So this is just a trivial rewriting, but now it already looks interesting because this ij are non-adjacent. Okay, one is between 1 and A, the other is A plus 1 to n. So you can just erase it and call it Cij. That's your pullback. Now you move this thing back, you move this term, this is the overall thing. In the sum, you can just put it here. As I said, this thing can be turned into a cross ratio if you want. You just put in the infinity n. But now it looks like a map. That's the thing I want to emphasize. So this Cij are constant, and for a given point in your positive part of your moduli space or just the worldsheet isotropyhedron, you find some point in this subspace, in this H. And what are they? Where are these points located? The only thing you need to show is that they are positive. Then by our starting point, that you need to show that they lie in this delta n. Since you are already in Hn, then you show they are in your kinematic isotropyhedron. But that's not enough. Now you only thought about this SA plus 1 in our new variable. They look like XAA plus 2, right? So you only proved, you can easily prove this now, right? If your sigmas are ordered, then both of these are positive. So it's positive. So you prove the XAA plus 2 is positive. But you need to do further. You need to put any XAB is now positive, right? Then you're done, because for any point in the M0n plus, if you go to any subspace Cij positive, if you can prove you are in this positive region, then since you're already in the restriction also to subspace, you're in a isotropyhedron. So I don't want to write down this formula. It's just a bunch of combination of Cij with some positive cross ratio actually. Okay, it's slightly more complicated than that. How do I get this guy? I just write remember this is just the sum of planar, it's just some planar variable, sum of p's between A and B. I can write it in terms of these guys and some non-adjacent guys, and non-adjacent guys are Cij again, right? So I just shuffle them in, and you show that this is a manifestly positive combination of positive cross ratios where coefficients are given by Cij. So this is the point that when I say I pull back my scattering equation to this subspace, I manifestly map every point in the worldsheet isotropyhedron now to the kinematic isotropyhedron. So you can say the following. So the scattering equation really provides you actually we conjecture to be a diffeomorphism from the M0n plus, which is a positive geometry, actually the compactification of that, to your kinematic space. This is provided by scattering equation map, which I just showed here, okay? So you can see that the map is really one-to-one in the sense that, so also when you go to every boundary of this isotropy, when some sigma pinch, only when the sigma pinch, you reach at some boundary of your kinematic isotropy where x can become 0. And the other direction is also correct. If you start with the scattering equation with all the xab positive, you want to solve for all the sigmas. Now you don't have to restrict yourself to subspace even. You solve them, you find n-3 factorial solutions. They are complex, they are complicated, but one of them, exactly one of them, lie in this M0n plus. So this is why it's a one-to-one thing. The second thing is only a numeric fact that we check up to 10 points. We don't know how to prove it that exactly one and only one solutions lie in this site. So that's why it's still a conjecture. But assuming this is correct, we have very strong evidence for this, then the construction of Nima and Yontao and Thomas Lamb told us that you can find a push forward from the canonical form of this guy, which we show is the Pactator form, to the canonical form of your kinematic isotropy, which is that form, the planar scattering form we studied yesterday and today. So this is a push forward given by this. So write it in the way you like. It's nothing but write it in the way that we showed yesterday. Is exactly just something I already showed you yesterday. The sum of solutions of your scattering equation of this Pactator form that I can write as dn sigma over SL2 with Pactator 1 to n is nothing but this mn with m-3x pulled out, right? So this is what I showed you yesterday as the equivalent statement of CHY, but now I promise that it has a geometric meaning, and the geometric meaning is given by this scattering equation one-to-one map. Okay? So there's something else I can say, since I still have some time, that so you can also pull back to different subspaces, and that will give you M alpha beta, as we discussed yesterday, right? So what happened there? So you say you want your scattering equation to map to this subspace that give you the same ordering as your moduli space, then you get the isotrohedron. If you map it to a different subspace corresponding to another ordering, you should get M alpha beta. But what's the meaning of that, right? We haven't really established. So in other words, if you have a so this is already in the subspace H of 1 to n, right? Now if you have a subspace that's different ordering than this, you should get M alpha beta times some wedge product as we shown yesterday. But what's the meaning of that? What's the geometric meaning there? It turns out it's just if you go to some other subspace, then what happened to your kinematic isotrohedron is some of its vertices got sent to infinity. So now it looks like some degenerate isotrohedron, which only has part of the. So remember the canonical form is summing over all the vertices. Now you are only summing over those remaining vertices, so which give you M alpha beta. It's just a subset of the thing you have. Okay, and another thing I want to say is that we do learn some property of the amplitudes. As I told you, now we have different triangulation and so on, but we also learn that, for example, you have new, we already showed you there are new representation of the amplitudes. There's another property that I would like to just simply tell you that I did not know about phi cube amplitude, but now it's becomes totally manifest from this picture. That property is the following. So if I give you an amplitude mn, you say, it's so trivial, it's just summing over planar graphs with propagator, right? Now I say in mn, let's send sum of the Mandel sum to 0. It almost looks like a soft limit, but it's not quite. Let's then say S13, S14, all the way to S1 n minus 1 to 0. Okay? Not S12 and S1n. They are special in this ordering. Anyone can guess what the amplitude becomes?
0.
Yes. So for 4 point, it's really trivial. You have 1 over S12, 1 over S1 over t, which is u over st, right? So I'm sending u to 0. So it vanishes. But already 5 point, it's kind of non-trivial to show this property. It's about the amplitude as a whole, right? It's not about every Feynman diagram. But the geometry makes this completely manifest. Why? Because these are exactly my C's. So I told you M is the dual volume of some dual associated region which built by giving a subspace labeled by the C's. Yes.
Is that an ordered limit, or how did you?
No, sorry. I'm sending everyone to 0. It doesn't matter which order they go to 0. Yeah. So if I do this, it turns out the geometry. What happens to geometry is the associated region collapses to a lower dimensional one. It's no longer even a 3-dimensional thing. So there's actually a better understanding now that we did more recently, that actually if you keep all the C, if you send all the C to 0 but only keep one of them non-zero, the associated region always collapses to a simplex of some dimension. The dimension depends on which C you kept. So in the end, I guess this is how our construction is equivalent to Alex in the generalized permutohedron in this special case, which is we can interpret the associated as a Minkowski sum of those simplices where we only keep one of the C non-zero. Okay? So if we do this for particle 1, we send all the C associated with 1 to 0. It turns out we collapse to a rather low dimensional guy which has a 0 volume. So this is completely trivial from the geometry point of view that we call, quote unquote soft limit of your of the phi cube amplitude. The second property, the last thing I want to say is that there's this projectivity we said yesterday, right? Projectivity, which means in this context, in general, it's related to the fact that you can arrange things in a BCG form for a general scattering form. But in this particular planar case, when you have a Jacobi identity, you only have at most 2 terms of them. The second term is not there. So it really just means all the coefficients are plus minus 1. You need to do a mutation when you go from one graph to the other. That sign needs to flip, right? So what's this projectivity really mean for amplitudes? It actually means something very similar in the n equals 4 case, that you have no pole at infinity, right? Your amplitude should not have pole at infinity. This is not manifest at all for every Feynman diagram. Every Feynman diagram has a pole at infinity. But now we understand it because our construction never introduced pole at infinity to begin with. It's projective. But when you triangulate it, you introduce that W star, which brings the infinity, such that every term is no longer projective. Actually, any combination of Feynman diagram is not projective until you add all of them together. So it's another property about the whole geometry that you cannot see from individual Feynman diagram. So how do you see them more manifestly? You can go to other triangulation. So those triangulation that does not involve infinity, it will be term by term manifest. So I'm very tempted to say that this is our dual conformal invariance in this rather trivial example, that BCFW make it manifest, while the Feynman diagram expansion is totally screwed. You cannot see it term by term. Okay, I guess that's all I want to say. Thank you.